In this session, we'll be having a quick overview of Verilog HDL. Here, HDL refers to hardware description language, which is used to configure FPGAs, which are field programmable gate arrays and similar systems. As programming is related to microprocessors and controllers, similarly HDL is related to FPGAs, which are electronic systems which consist of processors, then complex programmable logic devices, inputs, output terminals, ports, memory blocks, and the most important feature of FPGAs are parallel computing. In Verilog, the digital systems are treated as a module, which is as shown in the block diagram. So these basic modules, depending on the design suits what we are using, can be available as a schematic entry or a Verilog entry. In schematic entry, one can drag and drop the elements or the modules like logic gates and flip-flops. In Verilog entry, one can describe it from the scratch. Now consider a module as shown. So the digital system shown has terminals A, B and C, wherein A, B becomes input and C becomes the output, and it has its own functionality described in this block called system 1. So to describe it in Verilog, the keywords are module, then the system name, and in parenthesis, round parenthesis, we have terminals defined. Now to segregate the terminals as inputs, outputs, and then single bit or multi-bit, and various other attributes, we do terminal declarations, and then to describe the functionality, we have procedural block or the functionality. So for terminal declarations, the keywords which we generally use are input, output, and in-out, where in-out is the bidirectional port declaration. So for single bit variables, it is directly defined as input A, output C, and so on and so forth. If you have multiple inputs of same size, we can segregate, or we can write it as with comma. Similarly, for multi-bit, we use array definition, wherein as shown in the example, input 3:0, which we read as 3 down to 0 of A, it defines A as a 4-bit variable. Similarly, for variable C, it is 8-bit variable. And other keywords which we may use in the main body can be parameters and integers, wherein parameters are used to define generally the constants in the main body of Verilog modules. In the main body of the Verilog modules, and integers are used to define a variable which we want to change as per our requirement. And by default, it gets defined as a 32-bit variable if not specified, if the size is not specified. So other popular keywords which we'll be seeing in our further sessions are registers and wires. So let's go with the procedural block and functionality descriptions. So we have generally three kind of procedural blocks with Verilog. So let's see the first block, which is assign block. It is used to define the combinational expressions or combinational systems. In case if you have multiple assign blocks in the module, all executes parallelly, what we call as concurrently. So for an example, if we write assign, then C equal A and B defines an AND gate. Similarly, assign Q equals the statement, it defines a multiplexer. So if variable 1 is asserted, then output will be A, else B. So for initial block, it executes only at the start of execution. So we use this to generally assign the register variable in the module. So let's see an example. So if we write, or if we type in initial Q equal to 0, wherein Q should be a register because it is associated with some kind of storage like memory for the variable. Similarly, if we have multiple assignments together, we can wrap everything in begin and end. Note, To define multi-bit, we use the bit number, like it is 4 bits, so we'll use 4, then backtick, then B stands for binary, and then we'll have 0, 0, 1, and 0. So one can use decimal as well. So one can write D, and then directly one can write as 2. Similarly for 2-bit variables. So here, begin and end statements are used to wrap multiple statements with initial block. Coming to the always block, which is one of the most commonly used procedural blocks. Unlike an initial block, it executes forever, and it has sensitivity parameter listing as level or edge triggered. So as an example for level triggered, we have the example as shown, wherein we have always @AB, then output is defined as a register. Similarly, for edge triggered example, we have the part as shown. So here pause edge or neg edge, it refers to positive edge or negative edge. This block responds only to the transitions of variable listed as the sensitivity parameters. So for example, if we have always @A comma B and C equals A and B, and in other part if we write only sensitivity as A, then the systems are totally different. The first example, it defines an AND gate, which is a combinational system, and it is similar to the assigned block definition. But in the second part, it becomes a sequential system. The changes in C are only brought about by A, and the value of B is picked by the transition of A. So to illustrate that, let's consider this example. So in the example, red color is the output, and A and B are the inputs. So to check the functionality, initial changes in A are reflected in C, and similarly, the concluding changes in B are also reflected in C. But in the definition with only one sensitivity as A, we can see the clear difference. So changes in B are not brought about. The value of B is always taken as 1 because that was the transition of A variable here. Now consider the following declaration for the always block. Since here we have multiple statements, we'll be wrapping everything in begin and end. So these two statements are executed sequentially. So after C statement is executed, then D statement gets executed. So here the outputs have indeterminate state, that is a race around condition, because the present value of D is not yet defined. So every time this definition gives us indeterminate states. So this assignment is called as blocking type, which is indicated by equal to sign in the assignment. So to prevent this race around conditions, we use non-blocking assignments, which is described as or indicated as less than equal to as shown. So here the right hand side variables are the past value of the output which are defined as the registers, and each statement is executed parallelly. That is what we call as concurrent, and it is used to describe a sequential system. Apart from the logical descriptions, we have other various statements as well in the always block, like if, else, then case structures, then we have looping statements. So for example, we can have always of proper parameters, then we can wrap everything in begin and end. Then we can have conditional definition. Similarly with the case statement as well. So we started with the system description or the module description. So we are again checking up the idea of terminal declaration and the functionality. So we have seen these two parts. So let's take an example to illustrate the module definition. So we have the digital system as shown, whose specification is A and B and C variables are the terminals are single bit and system is an AND gate. So the description goes as shown. So we have module and then the declaration, and then we'll have input A and B and output as C. Since it is a combinational system, so we can use assign statement. So we'll write assign C equals A ampersand B. So this is the module description for the given system. So let's consider an involved system where my AND and my inverse are two modules which are included in the main module of my system 1. So a user may be tempted to draw the following description, which may be illegal or invalid. So the my system 1 is the module with the terminals as A, B and Q. Then we can have appropriate terminal declarations and the main body. And in case if a user gets tempted to type in the modules or define modules within a module, it is invalid or illegal in Verilog. So in order to realize this kind of involved module, we use module instantiation, a process of module instantiation, wherein the inner modules what we'll be using are already created separately, and then the connection between them will be mapped as a wire. So in case if we are defining the main module of my system 1, so apart from the terminals A, B and Q, we need to define the connecting terminal C as wire as well. So let's see an example. To define the same system, so we assume the basic modules of my AND and my inverse already created, and with the input arguments or the terminal order defined as shown. So a valid description in Verilog for this given module my system will be, so the terminals need to be defined, and then the instance, and then the connection between these two instances needs to be defined as wire. Now to instantiate, we call the main module name and then a temporary tag of module, let's say M1, and then in the order of the input arguments or in the order of the arguments for the main module, we need to pass the variables. So there exists special modules which are called test fixtures or test bench, which test the main module functionality. So these modules are without any terminals. So in the block diagram as seen, the green block diagram, we don't have any terminals. It doesn't have any terminals. So primarily a user sets various states or the signals for the inputs which are stored in the memory block. So we define the driving part for the input of main module as register variables, and then to collect the output which are as a result of the excitation of the main module to the input. So that will be defined as a wire variable. Output will be defined as the wire variable which are as a result of the input excitation. Similarly, so in most of the Verilog modules, the startup declarations can be seen is as shown. So this we are taking it here since in the test fixtures we need to create lot of delays and clocking schemes. So here the time reference actually it depicts the quantification of the delay parameter. For example, in case if you have this fraction apart from the module declaration, so we assume the appropriate declarations are done. And in case if we have hash 20 coming up in the test fixture, it is mere a count. and the quantification is amplified by this unit. So we have hash 20 implying 20 nanoseconds, since here we have time reference as 1 nanosecond. So similarly, we have time resolution as well, which dictates the step size or the resolution for the simulation run. So apart from the statements, what we have seen, there are a lot more in Verilog. For example, we have tasks and functions, which can be explored more from the reference materials as shown. So these are two popularly used texts for learning the Verilog, and then we have YouTube videos as well.